Hi students, I am answering some of your requested questions. I'm not going to answer all of them, and I'm not going to answer them completely because I'm going to leave some of the work for you. But this should get you started and maybe over the bumps you've encountered. So for 41, I'm going to leave it completely to be discussed in class by you. So if you had a hard time with 41, have another look at it. Think about Hooke's law and the energy stored in a spring and how that spring energy gets kind of transformed into gravitational potential energy or vice versa as the bungee jumper falls and the spring stretches and the kinetic energy of the jumper turns into spring potential energy, or I should say the kinetic energy and the gravitational potential energy of the jumper turns into spring potential energy. We're thinking conservation of energy there. But I think it would be beneficial for you to see your colleagues' solutions for number 41 in pieces in class on Monday. 52 and 53 are about conservation of energy, and they include issues of mechanical energy being lost to friction and or air resistance, but dissipative forces. So they're similar, but slightly different, of course, and I will talk about them here. 72 and 76 are of the sort of more complex problem section, and we will discuss them. I'll at least help you set them up. They are also going to be a discussion about conservation of energy. So let's start with 52. You drop a ball from a height of 2 meters, and it bounces back to a height of 1.6 meters. So we can imagine the ball at its starting position, it falls, it hits the ground, it rebounds to something slightly less tall. So we have our initial position of 2.0 meters, and then our final position of 1.6 meters. So if mechanical energy were purely conserved, if there were no effects of air resistance or heating as the ball squishes and regains its shape, we would expect the initial height and final height to be the same, but they're not. So what fraction of its initial energy is lost during the bounce? What's the ball's speed just before and after the bounce? And where did that energy go? So the first part, fraction of energy, let me make sure I'm using the right words. Fraction of initial energy lost during the bounce. And I use quotations for lost. It's not lost, we know where it is, but it's no longer held in the mechanical energy of the ball. So really we want to compare the final energy to the initial energy. And then we can multiply by 100 to make it a percentage. Actually, no, it's just asked for a fraction, so we don't have to multiply by 100. We're just finding the fraction, right? Final versus initial. And the initial energy before the drop is gravitational potential energy. The final energy at the top of the path, again, because at the top of the path the ball will pause, is also gravitational potential energy. So we really want to compare gravitational potential energy at the final versus gravitational potential energy at the start. So mg ending height, 1.6 meters, versus mg starting height, 2.0 meters. 1.6 versus 2.0. That's really what we're comparing because the ball has ended with less gravitational potential energy than it began with thanks to dissipative forces. So we have 0.8 of the original gravitational potential energy at the end, or 80%. We have lost 20% of the initial energy, and we have maintained 80%. Okay, so part B, what's the ball's speed just before and just after the bounce, and where did the energy go? So just before and just after the bounce, we think about how the ball has had to fall 2 meters through the pull of gravity. We could also consider how for the drop from 2 meters above, we had a transformation from gravitational potential energy, oops, let me write it as gravitational potential energy to kinetic energy. Either way, we get the same relationship that the velocity of the ball just before the bounce, or just at the floor, is equal to the square root of 2gh. And so we can find that the ball's speed just before it encounters the floor and the ball's speed just after it encounters the floor, assuming a sort of perfect condition bounce, is equal to the square root of 2 times 9.8 meters per second squared times 2 meters. And I have to flip my calculator. You should have a value of 6.26 meters per second. So plus 6.26 before it encounters the floor, and minus 6.26. Oh wait, flip that. Minus 6.26 before it encounters the floor, and plus 6.26 after it encounters the floor, having a switch in direction. Where did the energy go? So why did we lose 20% of the initial gravitational potential energy? We can assume that there is air resistance, particularly air resistance, and that the ball on its ascent back to its starting place has had some of its kinetic energy transforming into heat due to friction. Okay, so again, I'm trying to keep these videos to about 10 minutes. That seems to be the limit of what I can upload to YouTube in a timely fashion. So let's see if we can power through number 53, which is another question that involves friction. So 53 is a 66 kilogram skier starting from rest at the top of a 1,200 meter long trail, which drops a total of 230 meters from top to bottom, so something like this. We have at rest, which is telling us that velocity equals 0, kinetic energy equals 0 at the top. At the bottom, the skier is moving 11 meters per second. So the question is, how much energy was dissipated by friction? So if there was no friction, if there were no dissipative forces, I would expect the gravitational potential energy at the top to be completely transformed into kinetic energy at the bottom. So we can figure out whether that's true given the starting height and the ending velocity. Let's see, I did not write the skier's mass, 66 kilograms. And then if there is a difference, we can assume that the difference, the lower ending mechanical energy, is made up for by the work done by friction. So mgh versus half, right, it's more like a question mark, mv squared. So we have 66 and 9.8 because we're on Earth, and 230 meters tall versus 66 and 11 meters per second of velocity. So on the left-hand side of the equation, on the starting gravitational potential energy side of the equation, we have a value of 148,764 joules. And on the right-hand side of the equation, or the kinetic energy side of the equation, we have 3,993 joules. And those are definitely not equal to each other. So there has been a transformation from starting gravitational potential energy to partial kinetic energy at the end. But energy is never destroyed, or at least not in our current paradigm. And the difference has to be made up for by the work done by friction. So there must be 144,771 joules of energy difference that it has been converted to internal energy, temperature, by friction. That is our current model.